Good morning, scholars. Mr. Larson here. Before we get going on our next lesson, a deep thought for you by Jack Handy. Better not take a dog on the space shuttle, or for that matter, the SpaceX rocket, because if he sticks his head out when you're coming home, his face might burn up. Another deep thought brought to you by Jack Handy. Hey, today we are going to be doing something that I really find satisfying because there's just a real direct answer. It's clear cut. That's what I like. And it is our target for learning today has to do with just reminding you how to solve linear systems of equations. And of course, your worksheet, your homework will be a worksheet that's attached or linked in the folder. So just know that you're going to be remembering how to solve linear systems of equations by the graphing method. And there are actually other methods, but we're going to start with this one, and I'll mention them here, that this is the one that we're going to be talking about today, graphing, and we will be using our calculator. The next method we'll use is algebra, and then the last one is working with some matrices and some things called determinants and Cramer's rule to solve a system of equations, of linear equations. So with that, let me just talk about a strategy. When you're solving a system of equations graphically, what you are looking for is the place where they intersect, because where the two lines intersect is the solution for that system. So there are times when you have to estimate because it won't be precisely, the ordered pair 1, 1 or the ordered pair 10, negative 20. It won't be that clean. It'll be a decimal point or a fraction. So you'll have to estimate. So what I always suggest is whatever your answer is, verify it by checking it. And so I hope to do that for you and make sure that you see that what we find is actually the solution to the system. So to begin with, a problem. And remember, word problems I think are some of the most challenging. And so I won't make you set this one up, but you will get some problems like this that you will have to set up. So try to think with me how I came up with these two equations. The score on a trivia game is obtained by subtracting the number of incorrect answers from twice the number of correct answers. If a player answered 40 questions and obtained a score of 50, how many questions did the player answer? So in this first sentence, there's one equation, and in the second sentence, I think there is kind of a second equation. So let's start with this thing right here. The score. So we're at a restaurant. We're doing a trivia game. The score on a trivia game is obtained by subtracting the number of incorrect answers. Now we're going to start out by the strategy is start out by writing down what you are looking for, what you are being asked to find. And in this problem, we're trying to find out how many incorrect, how many correct. So we start out by writing down X is going to be the number of questions that we got correct, and Y is the number of questions we got wrong. And so what we do is I look back up here and it says the score is found by subtracting the number of incorrect from 2 times the number of correct answers. So that's where we get 2x is 2 times the number correct. You subtract from that the number of incorrect answers, and what we find out is that is going to be our score. Well, if a player answered 40 questions and obtained a score of 50, that's where this 50 comes from. So 2 times the correct answers minus the incorrect equals 50. And then we know that there are a total of 40 questions, and that's where we just take the number of incorrect or correct plus the number of incorrect equals 40. So we've got 2 equations, and what we are guessing is that wherever this intersects, that is the solution for both the top and the bottom, and that will be how many questions did the player answer correctly and incorrectly, but we just want the first one. So let's try to solve it. Remember, using our graphing calculator, we need to have it in slope-intercept form. So I'm going to take this 2x minus y equals 50, and I'm going to, I'm just going to add y to both sides, and then I'll be left with 2x equals y plus 50, and then I'm just going to subtract 50 from both sides, and what I end up with, excuse me, as my first equation is y equals 2x minus 50, or I could also write it y equals 2x minus 50. That's in this form up here. So I know that the equation is of the line has a slope of 2 and a y-intercept of negative 50. Then I'm going to take this other equation right here, and just simply I'm going to subtract x, and I end up with y equals 40 minus x. Another way I could write it, kind of right down here so that I have these 2 system of equations right next to each other, I could write it y equals negative x plus 40. Okay, so what I'd like you to do is get out your calculators. Find the on button down in the left-hand column, very bottom. Hit the y equals key and move your cursor over to the right and hit clear so that you have nothing on any of the y1, y2, y3 equals, any of those lines. What we're going to do is just type in y equals 2 and then the variable x in the second column, third row down. Whoop, let's see, I need to go back to y equals. And make sure that the cursor isn't on the equal sign, but that it's blinking y1 equals, and then it's blinking and kind of empty space there. So 2 times x, and then I'm going to subtract 50. That's my first equation. I could hit graph right away, and I can see that my window isn't quite right. And so what I would suggest is that we change the resolution of this, and our x min, why don't we leave it at, let's leave it at 50, and the x max at 50. Let's have the x scale be 5. And by the way, I made a mistake when I said that. The x min is going to be negative 50. The x max is positive 50. The x scale, let's say that that is 5. And then I think we can replicate the y min of negative 50 and the y max of positive 50. Now if I hit graph, I have a pretty good idea what that line looks like. But let's go back to the y equals, move down to y2 equals, move your cursor over so it's blinking in the open space, and then we want to type in negative x plus 40. And now I should be able to hit graph. And what I notice is that there are 2 lines now, and if I hit trace, you see the cursor kind of blinking, and when I stop, it I'm not sure I'm right on, but it says, like, down at the bottom of my screen, it says x equals 29.7, y equals 9.57. I think that was actually supposed to be an integer, a whole number. And so my guess is x equals 30 and y equals 10. I can't quite get on exactly the spot where they intersect. So, and I had done this before. And found out that the answer was 30 and 10. And remember, we're going to check our answer. And so the way we check our answer is putting it right back in the equation. And so 2 times 30 minus 10, does that equal 50? 2 times 30 is 60 minus 10. Yeah, that equals 50. So that seems to work in this equation. And then if I go in the second equation, 30 plus 10, does that equal 40? Yep. So we used our calculator. It just didn't quite, we couldn't quite trace it the way we wanted to, but it seemed to work out. I'd like you to do this one by hand to begin with. And then we'll do it quickly on the calculator. So we have two equations, 3x plus 2y equals -4, and the other one is x plus 3y equals 1. What we want to do is solve, put it in slope-intercept form, because when we do that, it's just really easy to graph. So this first equation, what I want to do is I just want to take 3x away, bring it from both sides. I'm going to move this up over here. And so I get 0 here. So I end up with 2y equals -3x minus 4. Then I'm going to divide both sides by 2. This cancels out. I end up with y equals, and I have to divide this 2 into both of these terms, -3x and -4. So I end up with a -3 over 2x, or I could just write -3x over 2, and -4 over 2, which is just 2. So that's my first equation. This one down here, right here, I subtract x from both sides. I end up with 3y equals -x plus 1. I divide by 3 on both sides. Notice that this cancels out, and I end up with y equals -1/3 x plus 1/3. Okay, so what we can do is graph these. I'm going to start by graphing this one right here. I'm going to go to -2. That's my y-intercept. -2 is right here. And the slope is down 3 and over 2, the rise over the run. 1, 2, 3, and over 2. Now what I do is I connect that as best I can. And draw the line. And then I'm going to do my other equation. Right here. And this one is a little bit more complicated because of the y-intercept of b. And this is my slope. So 1/3 is somewhere right in there. And then I go down 1 and over 3, down 1 and over 3. So anyway, it looks like this point right over here is the point of intersection. And if I was to guess, I'd say it looks like it's up at 3. 1, 2, 3, 4, 5, 6. Like positive 3 up and back 1, 2, 3, 4, 5, 6. So it looks like that's approximately where they intersect. Well, you can see when I did it before, I was way off. If I and you can see the reason of that is the line wasn't right on those 2 points, and it was 1/3. It was kind of quirky. So let's put those two equations in the calculator real quick. Turn your calculator on, hit y equals, move your cursor over into the, I think it should be on top of a 2x, and move it down to the second equation and hit clear so that you're all clear. And let's just type in these equations quickly. I'm going to go back up to y1 and type in -1 divided by 3x plus 1 divided by 3. And I'm going to move my cursor down to the second line. So I've just typed in this equation right here. Now I'm going to type in this equation in the second equation, and it's y equals negative 3 divided by 2x minus 2. Now I'm going to hit graph. And what I notice right away is my window is really kind of out of whack because we did it for that last problem about trivia. So I'm going to hit the second button on the top row, window, and I'm just going to change. A really typical window is -10, +10, 1, -10, and +10, and 1. So this is my X min, X max, the X scale, -10, 10 for Y max, and Y scale of 1. You could hit pause to get those to work and put in your window. Now when you hit graph, it is a little bit clearer where they intersect. It does look like it is at that point. Where did we find that? It does look like it is at -2, 1. Now, when you check that in the original equations, you'll find that, yeah, we nailed it. We got the right answer. So I'll just check it. This is my x value. That's my y. And so I go 3 times -2 plus 2 times y of 1 equals -4. Is that true? I'm checking this. 3 times 2 is -6. Plus 2, does that equal -4? You bet. So it works in this first equation. In the second equation, I go -2 plus 3 times 1. Does that equal 1? -2 plus 3 times 1. Does that equal 1? -2 plus 3? Yeah. 1 equals 1. So we just checked really quick how accurate we were. It's always good to check your answer. Here is the kind of the last topic that we'll be visiting about in this video today. And it has to do with being able to describe a system of linear equations. If two lines intersect like this, and it may not be in the first quadrant or the second, third, or fourth quadrant. I mean, it may be in any of those. What we say is when they intersect like that, there's exactly one solution. And that means that they are consistent. So when they intersect, we call that a consistent system of equations. And each line is independent in that they aren't the same line. If they are the same line, then those things are considered dependent lines. They just look a little bit different, but their true identity is the same line. And so the first type of solution that you are solving for is where they intersect, and that's They're consistent and independent. The second type that you might run into is that really it's the same line, it just looks different. It's been multiplied by something on both sides or divided by something on both sides to make it look like they're different, but when in essence it is the same equation, one line is graphed right on top of the other. There are all sorts of intersections. They intersect all over the place, so we call them consistent, but they're dependent on each other because really it's the same line. And the third type of system of equations has to do where two lines are parallel. And if two lines are parallel, they never meet, and so they are independent lines, but they are not consistent because they never meet. So this is just a way to describe it. A consistent system has at least one solution. Inconsistent has none. They never meet. An independent system is exactly one solution. A dependent is that it's a consistent system with infinitely many solutions. It's really the same line. They intersect all over the place. So if you want to pause and write that in your notes, that'd be a good idea. So let's look at this example. 6 minus 2y equals 8. 3x minus y equals 4. Hang on for a second, because something looks a little suspicious there. Because if I multiplied this by 2, it would be 6x minus 2y equals 8. Whoa, it looks like this may be the same line. And so we don't even need to graph it, because when it looks like this, and by the way, that's why it's good to put things in standard form. And sometimes I do like slope-intercept form, because then it's really obvious. But you put it in standard form and you can kind of see, hey, is this the same line? If it is the same line, they intersect all over the place. So they would be consistent and dependent because there are infinitely many solutions. They intersect all over the place. If it's graphed, if we did it real quick on our calculator, what you'd find is there'd be one that is this blue line, and then you actually wouldn't even see the second one. It would be right on top of the other. A second example like this looks like this problem. If I have negative 4x plus y equals 5 and negative 4x plus y equals 2, those look suspiciously close. So let's get it in slope-intercept form and see what the deal is. So if I add 4x here, I end up with y equals 4x plus 5. If I do the same thing down here on this equation, I end up with y equals 4x minus 2. What's the deal here? What does this indicate? They have the same slope. Do you remember what that means? They're parallel. So we don't even need to really graph it because they're parallel, which means that they are independent lines, but they never intersect. So it's called an inconsistent system of equations. They would look something like that if it's graphed. Okay, a word problem for you. You ride an express bus from the center of town to your street. You have two payment options. Option A is to buy a monthly pass and pay $1 per ride, and the monthly pass is $30 outright. Option B is no monthly pass, you just pay $2.50 per ride. What I'd like you to do is pause, write down what each equation means, and then try to write two different equations to describe this system. I'll let you pause. Thank you. Okay, what we're going to do is y is our total cost of transportation. X is going to be the number of rides. So let's look at option A. the total cost of the transportation is going to be equal to $30, that's the monthly pass fee, plus $1 times however many times we ride the bus. So really, I could write this equation as x plus 30, y equals x plus 30. The other equation is option B. It's $2.50 per ride. So the total cost of transportation is going to be $2.50 times however many times I ride the bus. So right away, I get two equations like that. Now I notice that the slopes are different, so they're not parallel. They will intersect someplace. And one has an intercept. And what's the intercept down here? There's nothing there. So would you agree with me that I could write that? So what we would say is that this is an equation with a y-intercept of 0. If I was to graph those equations, starting out with this one, the y-intercept is 30. I go up 1 over 1, up 1 over 1, up 1 over 1. Or I could go up 10 and over 10, that's 1. So here are 2 points that I could connect. And then, remember we said our y-intercept is 0, so, and then I have to go up 2.5 and over 1, up 2.5 and over 1, up 2.5 and over 1. And when I get that line, looks something like that. What I find is there's a point up here where we have a point of intersection. And it looks like it's at 2050. So what that means, if you go back to what we said, is y is our total cost of transportation. It looks like it's 50. And x was the number of rides. So when we have 20 rides, the total cost is 50, and that is the point at where these two lines intersect. So thanks for listening. You do have homework. There's a worksheet in your folder. It's the worksheet for 3.1, Solving Linear Systems of Equations by Graphing. You will need graph paper. It is linked. And it's in this folder for this day and also in your red folder. So thanks for listening and take care.